The title of this video is Understanding Process State in Windows and Linux. Welcome to our video series on operating system. In this video, we will cover introduction to the process state in Windows, process state in Linux, transition and memory access. Let's go into the video. Introduction to the process state. A process is an active instance of a program. It encompasses the program's code and its current activity. Processes are crucial in an operating system because they are the main essential that the OS manages for resource distribution and execution. Significance of a process. Resource allocation. The OS distributes CPU time, memory, and dev- devices to processes. Execution management. Processes are scheduled by the OS for CPU execution. Isolation and protection. Processes run in separate address spaces, ensuring they do not interfere with each other. Concurrency. Multiple processes can run concurrently, allowing to multitasking. Communication. Processes can interact with each other through mechanisms like inter-process communication. Overview of process state in Windows and Linux. Common process states. Both Windows and Linux have similar process states, though their terms and specifications may vary. New. The process is being created. Ready. The process is prepared to run but wait for CPU time. Running. The process is active, executed by the CPU. Blocked. The process is waiting for an event. Terminated. The process has completed its execution. The process states in Windows. Windows defines several process states. New. The process is initialized. Ready. The process is ready to run when compute CPU time is available. Running. The process is currently executing. Waiting. The process is waiting for a resource or event. Transition. The process is moving between states, often due to tagging. Terminated. The process has finished and is being removed from the process table. Process states in Linux. Linux provides detailed process states. New. The process is being set up. Ready. The process is waiting to be assigned to a CPU. Running. The process is executed on the CPU. Interpretable. The process is waiting for an event or condition and can be interpreted. Uninterpretable. The process is waiting for a hardware condition and cannot be interpreted. Stopped. The process execution has been halted, usually by a signal. Zombie. The process has finished execution, but its exit status has not been read by the parent process. This is the second part of the video, the process states in Windows. In Windows operating system, process can be in several different states. Understanding these states and how process transition between them is crucial for effective system management and troubleshooting. Let's divide into the various process states in Windows and the transitions between them. Process states. The new. The process is being created and installed. Ready. The process is prepared to run and waiting for CPU time. Running. The process is currently being executed by the CPU. Waiting. The process is not ready to run because it is waiting for a resource or an event. Transition. The process is in the middle of a state change, often due to tagging or swapping data between physical memory and disk. terminated. The process has been finished its execution and is being cleaned up by the operating system. State transitions and triggers. New to ready. Trigger. Once the process is installed and has all the necessary resources, it moves to ready state, waiting for CPU time. Ready to run. Trigger. The, the scheduler selects the process from the ready state to run on the CPU. This is based on scheduling algorithms on the process priority. Running to wait. Triggers. If the process requires a resource that is not implemented or immediately available, like waiting for IO operating operations, it moves to the waiting state. Running to ready. The process is preempted, often due to the scheduler's time slicing mechanism where the CPU time is shared among processes. The process moves back to the ready state to await its next turn. Waiting to ready. The event resource the process was waiting for becomes available, allowing the process to move back to the ready state. Running to terminated. The process completes its execution or is terminated by the operating system or another process. It then moves to the terminated states for cleaning up. Transition. The, this occurs during process like tagging, where parts of the processor's memory are swapped between physical memory and disk. The process is temporarily in a transition state until the operation is completed, after which it moves back to either ready or waiting state. This is the third part of the video: process state in Linux. In Linux, processes can exist in several states, each indicating uh, a different stage of execution or waiting. Understanding these states and the transition between them is crucial for managing system resources and performances. Various process states: new or created. The process is being created and installed. Ready or runnable. The process is prepared to run and is waiting for CPU time. Running. The process is currently being executed by the CPU. Waiting. The process is unrunnable. Currently runnable. Interpretable. The process is waiting for an event or resource and can be interpreted. Uninterpretable. The process is waiting for a hardware condition and cannot be interpreted. Stopper. The process execution has been halted, usually by a signal. Zombie. The process has finished execution, but its exit state has not been created by its parent process. Transaction between states and triggers. New to ready. The process create and installation are completed. The process is now ready to schedule for an execution. Ready to run. The scheduler select the process to run on the CPU based on scheduling algorithms and priorities. The process then moves from ready queue to the running state. Running to wait. The process required a resource that is not immediately available, such as waiting for IO operations to complete. The process moves to the waiting state until the resource becomes unavailable. Interruptible. If the process is waiting for a signal or an event, example a key pressed or network packet, it can be interpreted and worked upon when the event occurs. Uninterruptible. If the process is waiting for a hardware event, Example disk IO, it cannot be interrupted until the event completes. Waiting to ready. The event or resource the process was waiting for becoming available. The process moves back to the ready state, indicating it is ready to run again. Running to stop. The process receives a stop signal, example SIGS stop, causing it to halt execution and moves to the stop state. Stop to ready. The process receives an continuous signals, example SIGCONT, allow it to move back to the ready state and to be scheduled for execution again. Running to zombie. The process completes its execution but its exit state has been read by its parent process. It moves to the zombie state, awaiting the parent process to read its exit status. Zombie to terminated. The parent process reads the exit status for the zombie process, allowing the operating system to clean up and remove the process for the process table. This is the other part of the video. Here we know about transitions and memory access. State transitions and signals. In Linux process transitions between various states based on signals defined in the system library signal.h key signals and their effects include SIG stop. The signal stop a running process, moving it to the stopped state. The process is paused and no longer consumes CPU time, but it remains in memory. SIGCONT. The signal continues a stopper process, moving it back to the ready state. The process becomes eligible for CPU scheduling again. SIGTERN. The signal requests a process to terminate gracefully, moving it to the terminated state. The process can catch the signal and perform cleanup operations before exiting. SIGKILL. This signal for forcefully terminates a process, immediately move it to the terminated status. Unlike SIG term, the process cannot catch or ignore SIG kill and it is terminated unconditionally. It is terminated unconditionally. Detailed transition between states. Now to ready. The process created the process creation and installation complete successfully. The operating system allocates the necessary resources and process in place in the ready queue. Ready to running. The CPU schedule select the process based on the scheduling algorithms and the process priority. The process is then moved for the ready queue to the running state where it starts or resumes execution. Running to waiting. The process needs to wait for a resource or event such as IO operations to complete. It calls to blocking systems call and moves to the waiting state until the requirement resource becomes available. Running to ready. The scheduler permits the process often due to time sleeking a multitasking system. The process state is saved and it moves back to the ready state to await its next turn for CPU execution. Waiting to ready. The resource or even the process was waiting for becoming available. The process is then moved back to the ready state, indicating it is ready to run again. Running to stopping. The process receives a sign stop signaling, causing it to halt execution and move to the stopped state. It is often used for debugging or temporarily pausing a process. Stop to ready. The process receives a signed CONT signal, moving it back to the ready state. The process can now be scheduled for execution again. Running to terminated. The process finishes its execution or it receives a termination signal, that's SIG-TERM or SIG-kill. It then moves to the terminating state for cleaning up and removal from the process table. Running to zombie. The process completes execution but its exit status has not been ready by its parent process. The process enters the zombie state, allowing the systems to retain its execution information until it is read. Zombie to terminated. The parent process reads the exit status of the zombie process, allowing the operating system to clean up and remove the process from the process table. Primary and secondary memory access. Understanding how primary and secondary memory are accessed during state transactions is essential for system performance and stability. Primary memory (RAM) used for immediate execution and processing. Ready and running state process process in these states primarily reside in RAM. The CPU fetches instructions and data directly from RAM, ensuring fast access and execution. RAM is crucial for maintaining the activity working set of a process. Transition state. During transitions involved in a computation or context switching, the process working set remains in RAM for quick access. Secondary memory. The secondary memory is a disk storage. Used for the secondary memory is used for swapping, tagging, and file accessing. Swapping and tagging. When the system runs out of RAM, it swaps out inactive parts of processes to disk storage. This can happen during transition from running to awaiting or from ready to waiting. The swapper out data is stored in a swap space or page file on the disk. The mechanism is essential for handling memory overcommitment and maintaining system performance. File access. Process in the waiting state often wait for I/O operations such as reading or writing files on the disk. Disk access time are slower compared to RAM, leading to long wait times for process that heavily rely on disk transactions to or from disk. If a process needs data that is currently swapped out to disk, it must wait for the data to be read back into RAM, causing a transition from the waiting state to ready once the data is available. This can introduce latency, but it necessarily it necessarily from managing limited RAM resources. Thank you for watching my video. Please like, share and subscribe. for the next parts of the video, and we will continue these videos on operating systems. And thank you very much for watching.